Welcome back. With some of the more recent image restoration approaches, we are interested in obtaining an estimate of the posterior, not just its maximum value as with map estimation. Coupled with a hierarchical paradigm, prior models for all unknown signals are defined, that is, for the noise, the original image, but also for the point spread function of the blurring system for the blind restoration case. And also models are defined for the parameters which define such priors. Then the posterior for all unknown parameters is formed. Since its estimation is not directly feasible, an approximation of it is sought after. With such an approach, the original image and point spread function of the blur are estimated along with the unknown parameters, such as the noise variance, automatically based on the available data. Since it becomes a rather complicated estimation problem, we do not show any of the algorithmic details. Instead, we show some experimental results which represent one of the state-of-the-art results. So let us now proceed with the material for this segment. I would like to make a few comments based on what we have seen. In the previous few slides, we saw that the result of the maximum likelihood and map estimation resulted in some nice closed-form solutions. This clearly may not be the case and simply depends on the noise model and the image prior we use. So, depending on these choices, we may have to address some challenging optimization problems which are outside the scope of what we are doing here. The second comment is that in all these derivations, we assume that the image and noise covariances in the general case or the specific parameters alpha and beta were assumed to be known. So there are techniques to try to estimate such parameters offline, but in general, we need to address the estimation of these parameters as well. Also, we have been dealing with the non-blind restoration problem, according to which the blurring function H, the impulse response of the system, the matrix H are known ahead of time. But clearly, very often this may not be the case, and therefore one needs to address the blind restoration problem as well. This is a topic that has seen quite some activity, and there are techniques that first estimate the blur and then perform the restoration problem, so it's a separate and sequential estimation process. However, the last 2 points can also be addressed through the hierarchical Bayesian paradigm. I would like just to give you a flavor of this paradigm, just mention it, describe it at a very high level, simply because we end up with challenging optimization approaches in many cases, and this is something, again, outside the scope of this course. However, having this basic information, I believe that you'll be able, for those of you interested, to look into the literature and dive a bit deeper in looking at some of these very interesting and exciting results. What we discuss here is an extension of the material that we already covered. So we're interested in forming this joint distribution shown here, and it's a distribution of F, the unknown original image we try to estimate, H, the unknown impulse response of the degradation system, so we are addressing blind restoration here. This set omega, which incorporates all the unknown parameters, model parameters we introduce, so omega refers to as the hyperparameters, and Y is the observed noise and blurred image. Now, the hyperparameters are treated themselves as random variables, therefore we bring in information about them through their probability of omega. This is a hyper prior. So, according to the product rule of probability, we have that this joint equals the likelihood function times the prior knowledge we bring into the problem. And the prior consists of a prior on the original image F, a prior on the unknown impulse response of the degradation system H, and the prior on the hyperparameters. So if we look at, for example, at what we already covered, we saw that for the likelihood there was the parameter beta as an unknown. Beta minus 1 is the noise variance actually. The image prior involved the parameter alpha, and let's assume that we have a prior on H, a smoothness prior, for example, that involves another parameter gamma. Then the set of hyperparameters omega, it's simply these three parameters alpha, beta, gamma that also I need to estimate. So we try to draw inference again based on the posterior. The probability of the unknown parameters, again, the original image, the impulse response of the degradation system, and the hyperparameters given the observed image, according to Bayes' rule, is equal to this fraction. And depending on the approach we follow, we can draw inference again from this posterior function. So we've introduced two additional parameters, H and omega, but other than that, the framework is again an extension of what we already covered. It's called the hierarchical paradigm, Bayesian paradigm, because in the first stage we model the noise, the original image, and the degradation system, and in the second stage we model the hyperparameters through these hyperpriors. There are different ways to draw inference from the posterior we showed in the previous slide, one of which is again maximum likelihood. We try to maximize the likelihood function here with respect to the three unknowns, the original image, the impulse response of the degradation system, and the set of the hyperparameters. Clearly now there are three unknowns involved, and the optimization problem is more challenging. One general approach is to alternate optimization, so you fix two parameters, you fix H and omega, for example, optimize with respect to F. The result of the optimization is fixed on F, then let's say H is also fixed, and we iterate on omega and keep iterating this way. Similarly, a map estimate can be obtained by maximizing the posterior. It's shown here again. This is the numerator of the posterior. The denominator is independent of the optimization. This is now even more challenging than maximum likelihood. Again, three unknowns. Alternating optimization is again a general approach that one can follow. Both these approaches provide so-called point estimates, just one answer for the unknown parameters. One might be interested in obtaining an estimate of the posterior itself. In that case, one can follow a variational approximation approach to the posterior. So as the name implies, a function that is better behaving is used to approximate the posterior, and then this other function is optimized and provides the desired form of the posterior. This is advantageous because now one can obtain additional information about the estimation process and possibly pick different points to represent the restored image as well as the unknown impulse response. Alternatively, one could sample the posteriors through some Monte Carlo approaches, and that way an estimate of the posterior can also be obtained. In all of these cases, however, the resulting optimization is outside the scope of this course, but again, for those of you interested, I believe you have some basic understanding here of this material, and you should be able to go to the literature and look deeper into any of these approaches. As mentioned multiple times so far, the amount and quality of the prior information about the image, the blur, and the noise is of the utmost importance in establishing the quality of the restored image. When it comes to Bayesian methods, this prior knowledge is incorporated into the algorithm through the use of prior models. We discussed such prior models for the noise and the image in previous slides. Another image prior model is the total variation model shown here. It has become very popular recently in the restoration literature because of its edge-preserving property by not over-penalizing discontinuities in the image while imposing smoothness. Z of alpha here is the so-called partition function. Delta of IH is the horizontal gradient at the ith pixel, while delta IV is the vertical gradient at the ith pixel. This actually represents the quadratic approximation to the TV prior, and alpha is the hyperparameter that needs to be estimated. When it comes to modeling the blur, one of the models that has been used is also a SAR prior on the blur. As we discussed, such a model imposes smoothness on H in this particular case. It's a reasonable model for a good number of the blurs that we encounter in practice, like the ones I showed at the beginning of the restoration segment of the course. So here the hyperparameter is denoted by gamma, and it needs to be modeled and estimated through this Bayesian framework. The literature is rich with prior models for both the image and the blur. It maybe goes without saying that the more complicated, mathematically speaking, the model, the hopefully better the results, but also harder the optimization problem one has to solve. In the following, I will show some experimental results when these two priors are used, the TV for the image and the SAR for the blur. I will not show any of the mathematical details. This variational approximation approach that I mentioned in the previous slide is utilized, but again, the main point is just to give you a flavor of what is achievable. I will show here in a synthetic experiment results, blind and non-blind restoration results, utilizing the variational Bayesian algorithm that I just mentioned a few slides earlier. The results are fully automated in the sense that all the parameters that are needed, such as the noise variance and the image and blur model parameters, are estimated automatically from the data. So we show here the degraded image. The blur has Gaussian shape and variance 9, and the blurred signal-to-noise ratio is 40 dB. This is the result of blind restoration when SAR models are used both for the image and the blur. When now a TV model is used for the image while the same SAR for the blur, this is the result we obtain. And if we perform a different implementation of the TV image model, we obtain the image shown here. By comparing the blind restorations here, most probably one would agree that the TV provides better restorations, the TV image prior, and this is also reflected by the improvement in signal-to-noise ratio number. Now, if the blur is known, and this is a synthetic experiment, so we know exactly the blur, so it's a non-blind restoration, then these are the corresponding results we obtained with these three combination of models I showed here. Let me switch back and forth a few times to see what is the additional improvement one obtains by knowing exactly the blur. So a similar comment can be made here that the TV image prior provides better results than the SAR image prior visually, and also by comparing the ISNR numbers. Actually, you see here the piecewise smooth result when you look at the TV results. That is the is what the TV model really promotes. We show here in red the original point spread function of the degradation system. I drew over it so that it's visible. And then below you see three different estimates of the blur when the blind restoration algorithm is run. And the differences are in parameters that one has to choose in determining the hyperpriors, the priors we impose on the hyperparameters that we need to estimate. So by and large, all these three estimates shown here do a reasonable job in approximating the real or original point spread function. We finally show a state-of-the-art blind restoration result utilizing the variational Bayesian framework I just mentioned a few slides earlier. A sparse image prior is used, a so-called super Gaussian prior, since we are modeling the edges of the image, which are sparse. We will be actually talking about sparsity during the last week of the course. So here is the acquired image and some close-ups. This is an image I also showed at the beginning of the lecture on restoration. This is actually the building outside my office here at Northwestern University. So while the picture was taken, while the aperture was open, the camera moved or shook in an unspecified way. Applying this fully automated algorithm, that is, all the required parameters were estimated from the data, here is the restoration we obtained. So quite a lot of information is revealed, looking also at the close-up windows down here. We can see the people, the three people walking there, and a lot of detail. The estimated blur is also shown here. So the shading of the camera did not follow a linear trajectory, as was the case with the horizontal motion blur we studied earlier.